Let us look at the same circuit. Now we want to solve for I1 and I2 using a super mesh. We will employ our standard 4-step procedure. However, we will update our number of KVL equations needed to solve for our mesh currents. Step 1 is to construct n minus n sub c KVL loops, such that we will construct one KVL loop that spans meshes 1 and 2, bypassing our current source. Step 2 is to assign our voltage potentials associated with their passive sign convention as to not duly label any elements. Now, since mesh 1 and mesh 2 are going to be constructed as one big KVL loop that bypasses our current source, we no longer have to assign a polarity associated with our current source. That is, we have V1 associated with our 9 ohm resistor, V2 associated with our 3 ohm resistor, and V3 associated with our 6 ohm resistor. Step 3 is to construct n minus n sub c KVL equations describing each mesh current. And recall, we defined our one KVL equation spanning meshes 1 and 2, bypassing our current source, such that our KVL equation becomes the following. Minus 12 volts plus V1 plus V2 plus V3 is equal to 0. Step 4 is to apply Ohm's law to express our voltage potentials in terms of our mesh currents and resistances, such that we have the following. I1 times 9 ohms plus I2 times 9 ohms is equal to 12 volts. Now we have one equation, two unknowns, and we will provide our second equation by our current source equation, which is I2 less I1 is equal to 1.5 amps. We recognize now we have the same system of equations we did previously when we constructed our system of equations without the use of a super mesh. It is noted that this method is easier, for we do not have to describe our voltage drop across our current source that shares mesh currents I1 and I2, and then relate those two within our KVL equations. Rather, we construct one KVL equation and one current source equation.